Hey guys, what's up? Eddie Yahoo here with KissAnalog.com. Alright, so today what I'm going to do is I'm going to compare the FFT of the MicSig, the GWInstek, and this Siglent back here with this Pico that's buried underneath all these probes. Got a couple experiments going on, and I did a video, just released it today actually, and what I used is this Unity generator to put out a 1 kilohertz, 1 volt RMS signal, and then I put on top of that 100 kilohertz 1% modulation. So if you're just looking at a signal, it look like 1 kilohertz. If you kind of zoomed in, you might see a little fuzziness. If you got closer, you could go, oh, there's a sine wave on top of that. So I wanted to compare the 8-bit of these other scopes to the 12-bit of the Pico to see if that extra 12 bits, or that, extra 4 bits, helped see that signal a little bit better. Now, so 1% is about 10 millivolts, and I'm not sure. I got to tell you something. I'm not sure about the Unity, how capable it is to put out a very clean signal, set up the way I had it set up. So, yeah. I don't think we saw something close to that on the Pico, so I think it's got to be pretty close anyway. So this video, what I want to do is I want to compare the FFT and do the same thing. See if this 12-bit does a better job. Now, one thing I can tell you, I think you maybe have noticed, is the software zooming in on waveforms, looking at things is really quick, really easy with the Pico. So yeah, I'm quickly becoming a fan of the PC-based box here. Honestly, in the past, I never really gave it much thought. But yeah, I've got a couple around here. I just really haven't used them yet. So I got this Pico, and yeah, I'm very impressed so far. So let's jump into this and see what we see on FFT. Alright, now we're on the GWInstek. So there's the 1 kilohertz signal with the 100 kilohertz 1% modulation on top, which is hard to see from here. So let's go to the spectrum mode. Alright, it's talking about the resolution. Well, here, let's go to channel 3. Okay, there we go. Oh, there it is. Popped up that here. Let me get rid of those cursors for now. Alright, so let's see where we are. The span, we're center frequency 100K, 10 kilohertz span. That's pretty cool. So each grid is 1 kilohertz. So there we go. There's our signal. Let's see if we can get a measurement for math. We have a different way of doing it. Okay, we're 20 dB per decade, which is fine. That's good. Noise floor is below 80. That's really good. dB volts, RMS, that's all good stuff. Bandwidth, let's see, that marker went away. Well, it actually still does have the little red exclamation mark. It's hard to see there probably. 2 hertz. Okay, so let's go back and fix that. Let's go to bandwidth. Okay, so let's go to, there's manual, it's 2 hertz. We're going to set it automatic, and let's see if that corrected it. Yeah, it went away, so we're 5 hertz resolution. So that's pretty darn good. There's our 2 little spikes there. And if we go to their search table, what we do, let's go to threshold and see when I move this right here, it's going to show us 2 peaks. So then, right now it's just saying we're picking 1. Okay, now we got 2. Okay, let's go to the peak table, and there's the measurements right there. Minus 46.4 dB. That's how we do that. Now let's go to look at the 1 kilohertz signal. So let's go to frequency and span. Let's do start frequency. Let's just do 100 hertz maybe. Stop maybe 10K or something like that. Yeah, we could even go a little higher resolution if we wanted, but that's probably good enough. What I mean is we go to 1K and then step that up to say 4K or somewhere around there, or even 2K if we want. that should put the thing close to the middle. And then at start, I'll just get that to close to 0. There we go. 1K. Span is just about 2K. Okay, right now, it just looked kind of funny. I went to this. It's because the averaging is on. So it's averaging the signal right now. There's a max peak hold on. Let's just go to normal. There's my orange waveform. Okay. You see all the information down here, the span, the bandwidth, all that stuff. Okay, so let's go to this search table, turn it on. And method, well, we only need one, I guess, since we only have one peak. And the threshold is right there, my level. So I'll just put it up here. See, if I go above, there's nothing higher, so the arrow goes away. Once I bring it down, it catches that one. So let's just go see what that is. And it's minus 1.6 dB at 999.5 hertz. So essentially 1 kilohertz. So that's how we do it on the GW. Spectrum makes it a little bit quicker and easier than the Siglent or the MicSig probably. I'm going to turn off the cursors, just get them out of our way. Okay, so here's our two signals right here, and that's 1%. So that's you know, supposed to be about 10 millivolts, but let's go ahead and change that amplitude. Okay, so I'm going to change the depth of our modulation from 1% going down to 5% right there. So we're still detecting them. You can see them dropping. We're going to go down to 2%, and there's 1%. I went to 0, but I'm back up to 1. Now, at 1%, they're just barely noticeable, right? But you can detect them. When we were looking in the last video, when we were looking at the time domain and trying to pick out that ripple on top of the AC waveform, it was really hard to detect anything. But here, the spectrum actually is able to pick them up. So I'm going to pull up my table thing again, and let's take this threshold right down to there. I mean, it's almost noise floor. See, the noise floor is right about there, minus 79, almost minus 80 dB. But I'll come right up here where I get two peaks. And let's go look at the table. Look at that, minus 66 or minus 67 dB, minus 68 dB. So it's pretty amazing that your 8-bit scope, even though using the time domain in the last video, it was so hard to detect any of this 100 kilohertz modulation, but here on the spectrum you can see the modulation. Now in this case, it actually looks like the 100K is being modulated by 1K, right? We're getting 99, 101. So like I said, you look at it either way, but yeah, so pretty cool, right? Alright, now we're on the MicSig. It's saying 1 volt RMS reading here, 1 kilohertz, but we have the 100 kilohertz, 0.1% modulation on top. So let's just go to our FFT, go to math. Alright, and let's see, we got that going. Here, let's see if we can. Okay, there's the 1 kilohertz signal. Okay, it's a dBs, channel 3, Blackman. Alright, and it's 20 dB per decade, so we could change that to match the other ones, or go 20 dB, I guess. Okay, and then I'll just grab that, pull it down, so it's putting the reference right there. And if I go to channel 3 and get more cycles, we get a little more resolution on the FFT. Okay, so let's go right about there, I guess. Turn that off, and there we are. So let's see if I can do a measurement on math. Okay, I've got max. Let's do RMS. Okay, I'm not seeing it pick up a measurement yet. Okay, I do have the cursor on there. And that's giving me about 1.2 dB. But yeah, I don't know how well I got that cursor on there. We can spread it out, get a little better look at it. Yeah, I'm not sure why I'm not getting a measurement. Okay, over here, it's saying it's frequencies 1 kilohertz, amplitudes 2.32 dB. Okay, you know what? Let me see if I can get... Okay, I do have the highest memory set. I was just looking up here to see where that was set. So that's the most memory I can get. So that, yeah, it's looking pretty good though. I mean, okay, let's go see if we can look at the 100 kilohertz thing. We need more dBs per decade. Okay, I'm going to move this guy over. And I see him right there. So I'm going to pull those guys over in the middle of the screen. Then I'm going to spread this out. Now one thing I want to note is 20, 40, 60, 80. This is showing noise floor like close to 90 dB. And it's showing these signals. I'm not sure why my math isn't working on them. They're right about 46.4 dBs, I think that is. This top weight measurement here. So minus 46.4 dB. But yeah, you could zoom in on just one of those peaks or zoom it out, get a little more resolution in between. The MicSig, I think, makes it pretty easy to move around and see the signals. I think I'm having an issue picking up math readings right now. Not sure what the issue is there. Alright, well, I just wanted to show you how you would do it on the MicSig. So there we go. Now that's 1%. Let's drop it down, see what happens. There's 5%, 3%, there's 1%. So it looks like it works all the way down to 1%. And if we take a reading on those, they're about minus 65.6 dB. So yeah, looks like the MicSig's capable of doing it. Alright guys, so here's the Siglent. It's taken me a while to set it up, but this is the 1 kilohertz waveform, and it's 20 dBs per grid here, per division. So 0 dB is right here, and we can see it's close to 0. The measurements, they allow one measurement in FFT, in the math mode, and I'm getting 0.37 dB, so minus 0.37, by the way. See the minus sign there. So that's what it looks like, and that's what the resolution. Here I'm going to show you one thing. Display exclusive. It's nice that you can get just that, but if you want to see the full screen with both waveforms, now see all the waveforms I have up here? That's what you want to have to get a good resolution. Let me take you to, there's 3 pages on this FFT. See the center frequency is 1 kilohertz. That's where we are, 1K. 500 hertz per division resolution. So let's see if I can get any better than that. Whoops. Okay. 500 is good, but if I get some more cycles, let's see if that works. Okay, I don't, yeah, there we go. There's 200. So you have to get, the more cycles you get, the more resolution you get. Okay. Now let me go back and get rid of that. There's split display. Takes a while to do all the math with that resolution. Okay, it was in roll mode. I took it off roll mode, and there we go. Okay, so then we get the exclusive display, and we're kind of reaching the max, I think, on this. It's just, we might be able to get more resolution. It's going to take a long time to update and all that kind of stuff. So anyway, that looks pretty good. So now let's go look at 100 kilohertz. What we're going to do is we're going to go to, let's see, this is page 3. If I hit auto set, I'm going to go ahead and do auto set, just show you what it does. maybe it's done. I think because I already had, I've already got close to where I wanted to be. I think it takes that into account and tries to see if it can make it any better for you. Because it did change it, but it didn't make huge changes. We're still just looking at the 1 kilohertz wave. So, okay, what we're going to have to do, okay, let's go center to 100K. There we go. Okay, now I'm going to use those cursors and move them over. You can kind of see what I'm getting to. It looks like, okay, there's that one. And amplitude, I can move that up. Whoa. That's the only thing about this scope that I really wasn't happy with, is this knob. It's just so overly sensitive. Okay, so that level is minus 45 dB. The other cursor's on 40, so it's minus 45 is where those points are, I guess. And so I think that's just the resolution we can get with this, but yeah, there's 1%. Now let's go to 0.1%. That's the real question, right? Okay, there's 0.5%. Takes a moment after I move it for the capture to pick up, so there's 0.1%. So yeah, I think at 0.1% the Siglent completely loses it. I'm going to go to 0.2. Now we have the cursor, so we know we can see one of the peaks right there. But it's really hard to know what you're seeing at that point because it's almost at the noise floor. So you'd probably be right there for a moment. It picked up 2. Okay, here's 0.3%. Okay, so it looks like maybe at 0.3% we're getting a consistent spike at 99 and 100 kilohertz. And that's right down at about minus 56.8 dB. So I don't know. So yeah, the Siglent can't quite pick up the 0.1, but it can pick up 0.3. Alright guys, thought I'd do something different. I'd just record the screen this way instead of having the computer record it, so I can kind of point to things. It's probably better the other way, right? But I just want to show you the graph down here really nice. It's 200 kilohertz, shows you the frequency, shows you the decibels up here. I mean, we can see our two frequencies right here, 99 and 101K, and then also our 1 kilohertz signal right here. So I mean, if I want to zoom in on the 1 kilohertz, I could just come over here and zoom on it like that. And then it shows my window here. It shows where I'm zoomed in. And look at that. It's 0.142 decibels minus 0.142. Now, if I came up here, here's a Blackman, logarithmic, all that stuff. I could select more points, but boy, I'll tell you what, it really starts to slow down because there's so many samples being taken and the measurements. But what it does, here, get rid of that again. What it does is it drops the noise for it. Look at this. We're down right here almost like around 90 dB. And look, that's only that many points. If I just double that again, it takes a moment. But you see, now this is auto scaling because I've got auto scale set right here. So, but look, we're getting close to 100 dBs here. So I'll choose another one. If I drop down to 1 meg, the max, man, it really takes a long time. But you can see how it's pushing the noise floor down every time I get more samples. Here's 110 dB right here. Wow, look at that. It just keeps on going down. So that's the advantage of using more points, yet look how narrow these spikes are. Boy, look at that, almost 110 dB. And look at our signals way up here. That's just a crazy amount of resolution. Okay, I'm going to jump to 14 bits, and see how long that takes. That should push the noise floor down. Yep, you just saw it push down a little bit more, right? I mean, yeah, just, it's really nuts. So here's our signal up here again. I'm going to zoom in on that again now that we've got all the, okay, there we go. So look at this. It's, and it puts a little cursor right there. It looks like where I think that's where 0 dB is. I'm going to put that right up on the line. Yeah, that's 0. And now it's going to take a minute for it to do all the math and settle in. See this whole picture adjust. Yeah, and especially when I'm zoomed in like this, it just slows things down, but it's just, that's just a crazy amount of resolution if you want to do it that way. Obviously it goes slower, so maybe if you want to do it just before you take a picture and then, you know, cut down on the resolution while you're playing around. Here, I'm going to get rid of this guy. And it drew all that back in. Let's go back to 12 bits for now. And we're back to 200K. So you know what? I'm going to just zoom in on these two guys, okay? And you know what? We're going to cut down on how many. I mean, that, look at this noise floor. It's down at 106 dB. I mean, that's just absolutely crazy. Actually, you know what I want to do is I want to do some measurements. Let's go add some measurements. And we're going to amplitude at peak. But let's do ruler number 1 so we know which measurement we're taking. And I'll take this ruler number 1 and I'll put it right on the peak. And down here it's doing some math. Okay, the initial value is 106. Okay, there we go, because it was looking at the noise floor. I mean, man, down at 106. And now we got minus 47.99 dB. Okay, let's add one more measurement. And let's put it near ruler number 2. Okay, and we'll take this box, put it right there, and I'll grab ruler number 2, move it over by the second peak. And up here you can see my rulers, 99K, the other one's 101K, 2K between them, the difference. And down here the measurements. And there's an average. This guy's going to take a while to average all this, but right now the min and the max is around minus 48 dB. So see, it's taking, every time it takes a reading, it's going to average that out. Right now there's 32 dB of error on the bottom one. The other one's 17 dB. Pretty soon though, they'll get that number down real low. But it's because I've got so many memory locations, you know, chosen. I mean, like 1 million. That's just a lot. And really the advantage is there's a certain point where the signals are narrow enough that you can see resolution between one signal and another, but it also pushes the noise floor down. Let's go ahead, that's 1%, right? So let's drop that down to 0.1. And there's 0.1. Now, it's going to take a minute. Here, you know what? I'm going to speed things up because that's just a lot more resolution than we need. And look, we're at minus 67. I'll move the signals away so you can see the cursors away. We should still get measurements close to those cursors. So we'll see if that, yeah, looks like it's still getting the minus 67.8, minus 68.7 on the other one. But yeah, look at that. So that's 0.1%. Those peaks are way up there. The noise floor is down here below 90 dB. Now I can just get a little bit more resolution, just go one spot more, and see how these get narrowed up. Still going pretty fast, so I can go one more, and we still got enough speed, and we got super good resolution. So that's the power of, actually that's the power of the Pico scope and the software, but also that we can get that, the peaks that far above the noise floor at 0.1% depth, you know, on our amplitude modulation is pretty nuts. Now there's 12, let's go to 14 dB. Let's just see what that looks like. Wow, it's so we're getting around, you know, minus 68 point something dB, those two peaks. Alright guys, so what do you think of that? It's pretty cool, right? FFT is pretty darn powerful. Hey, by the way, I want to stop and thank my patrons. Really appreciate all your support. And you become a patron for as little as $1 a month. Thanks guys. Hey, and you can support the channel for free. Thumbs up to the video if you liked it. Yeah, this video actually took a little while to do. Playing around with these scopes FFT. I gotta tell you, the spectrum on this guy makes it easy. The MicSig is actually pretty easy too. And the Pico is simple. Pico is very quick, very simple. So yeah, quick becoming a big fan of this guy. 12 bits, pretty nice. Pulls that signal right out of the grass. It pushes that ground floor right down, right? So pops that signal right up out of nowhere. Plus, you know, it's capable of grabbing it. Now, I was a little surprised on the Siglent that it couldn't get it in FFT. The ground floor is a little higher. It could be because that's not a 1 meg point scope. These two are. So, and the Pico, you know, it's well, it's just really nice scope. So anyway, I just wanted to see, you know, how, you know, if someone is trying to decide, hey, do I want to spend extra money? Actually, these two scopes, the Pico and the GW, are about the same price. So if I were buying one today, I'd certainly buy the Pico. Yeah. I like that GW. It's a great scope. But man, this Pico's, the software is super powerful, super fun. And the one thing I want to point out though is even with 8 bits, isn't it crazy how when in the time domain in the last video, I know that the ripple is on top of the 1 kilohertz signal, right? And I could find it in the case of the 1%, but in the 0.1%, I really couldn't find it. But, and even on the Pico it was difficult. You could kind of see a little bit of a modulation, but it's really difficult. FFT, they pop right out. So that's really interesting. I don't know why that is, honestly. I don't know if it's oversampling, which I kind of believe might be what it is. That they're sampling and they're oversampling. I don't know. I'm not sure. I'm just guessing. But somehow I've noticed for a while now, using the spectrum on this, the FFTs, I used FFT on this guy too, and I was going to add that in the video, but just didn't want to make it too long just to show you the capability. There's some measurement techniques on the FFT on the GW that's nice. That's a little nicer than the MicSig, or especially the Siglent, I guess. But so the GW is, I think, the most capable scope of FFT in the spectrum. It's a MDO, mixed domain scope, so that's what it's meant to do, and that's why the price is up there. It costs more than the rest of the scopes. Well, it's on par with the Pico, but yeah, like I say, now it is a 200 meg bandwidth scope, so you got to take that in consideration. This is a 20 meg bandwidth. Another interesting thing about that, though, maybe even ironic, is that we all want these wide bandwidth scopes, and in the lab at work we use scopes that are gigahertz bandwidth. Actually, the last one I wanted, the one I asked the equipment manager to pick up for me, was a Keysight. I really like that scope, and it's still a really expensive scope, but it was, I think, 500 megahertz, which seems a lot compared to these scopes, but compared to the other scopes in the lab, it's not fast. But okay, so the ironic part is almost all of us always put that 20 megahertz filter on right away, because it just filters all that crap, all that high frequency noise, all that stuff that your scope probes pick up. A lot of times you want to see exactly what you can try to see, you know, at the output, so use those little spring clips. You get rid of the little ground thing on your probe, and you really try to get the detail. Other times we kind of know that that little ground strap's going to pick up some noise, and yeah, we don't really care because we're not really trying to quantify that, so we just put on those filters. The MicSig and the GW are nice that they have filters you can set up, and obviously the Pico anything these scopes can do, the Pico can do that plus more. I mean, that software is just crazy. So really become a fan of that. Alright guys, making the video too long. Thanks for watching, and what do you think? Let me know what you guys think down below. Thumbs up to the video, I appreciate that, and hey, we'll see you next time.